Hi everybody, I wanted to talk to you all a little bit about your next online experiment. This online experiment is all about enthalpy of reactions. You've probably talked about enthalpy in your lecture course. You might have referred to enthalpy as delta H, or a change in enthalpy. And enthalpy is effectively just the heat of a reaction. Now, one of the things that's worth noting about enthalpy and enthalpy changes of a reaction, and one of the things that we're going to be investigating with this, is a process or is a concept known as Hess's law. Now, Hess's law states that if a chemical reaction can be written as the sum of two or more steps, the enthalpy change for the overall reaction is equal to the sum of the enthalpy changes for the individual steps. INDIVIDUAL steps. So whenever I think about enthalpy changes, whenever I think about Hess's law specifically, what I always try to do is I come up with a little bit of an analogy for it. So I like to think about it as if you and a friend are traveling from San Marcos to, let's say, let's go with Ames, Iowa. Okay. Now, you might have the directions to get from San Marcos, Texas to, let's go with Lincoln, Nebraska. I can't spell right. Okay, Lincoln, Nebraska. Okay, now that's not going to get you your final, your targeted destination of Ames, but your friend has the directions on how to get from Ames to Lincoln. Now, y'all are intrepid individuals, and you can see, oh, well, if I know how to get from San Marcos to Lincoln, and my friend knows how to get from Lincoln, or from Ames to Lincoln, well, then all that I need to do in order to come up with my entire pathway is basically look at the directions that my peer has and basically do them backwards. And so essentially what you would do is you'd be looking at your maps, your two different maps of San Marcos, Texas to Lincoln, and then Ames to Lincoln. And all that you would really need to do is to take this second kind of reaction or the second map and write it backwards. So Lincoln to Ames. And so you'd be able to basically bridge the gap and say, okay, well, I'm going to go from San Marcos to Lincoln to Ames. Okay, that effectively would give you your overall reaction of San Marcos, Texas onto Ames, Iowa. Okay. Now the same thing can basically be said about chemical reaction. To illustrate that, we're going to look at a couple of reactions. Okay, so we've got a total of 3 different reactions. I'm going to call them A, B, and C. And then with each of those reactions, we're going to have a delta H, change in enthalpy for these different reactions. And for some of these, well, they're going to be reactions that release heat, and some of them are going to absorb heat. So that delta H, if it is positive, that means it's absorbing heat, 393.5 kilojoules per mole. The second one, 74.6 kilojoules per mole. And then the last one here is, well, this is a negative 484.3 kilojoules per mole. Now I understand I haven't written any specific reactions, but I'm going to do that in just a moment. Now, each of these reactions, what they're going to be is they're going to be kind of my partial reactions, and they are going to combine together to make this overall reaction. CO2, gas, plus CH4, also in a gaseous state, yields CH3, COOH, which is in a gaseous state. Okay, now this overall reaction, I don't know the enthalpy change for that overall reaction, but I have these 3 partial reactions that I'm going to be filling in just a moment, and I can see CO2 is my first, is a gaseous substance that will break down to solid carbon plus O2. And that specific reaction has a delta H of positive 393.5 kilojoules per mole. My next reaction is CH4, gas, is solid carbon plus 2H2. That's gaseous. And that is also going to have a delta H that is positive, and that's 74.6 kilojoules per mole. Now my third reaction here is 2C sub S plus 2H2 gas plus O2 gas yields CH3 COOH gas. Okay. Now, when looking at all of these different components, at all of these different variables, what's important to recognize is, well, and what's important to think about is, what is my aim? My aim is to get these 3 reactions to be arranged so that I can combine them to give me that overall reaction. Okay, so what does that mean? That means that within these top 3 reactions, I need to have as reactants CO2 and CH4. Okay. Within these top 3 reactions, I need to also have in one of them the CH3COOH, also known as acetic acid, in its gaseous state as a product. Okay. Now, this particular example is kind of straightforward and simple because of how it's positioned. I'm going to do another example after I've done the demonstration of the lab itself, but essentially what I can do with this in order to solve my delta H is I'm simply going to highlight where all of my different reactants are. Okay, so the first reactant I'm going to do is I'm going to highlight the CO2 gas as a reactant. Now, as I look across all 3 of my reactions, my partial reactions, I see that I have CO2 gas as a reactant in that first reaction. Now, as I look across all of the others, first I'll look at the reactants and then I'll look at the products. Reaction B, CH4 is my reactant. Okay, that's not CO2. Reaction C, carbon and hydrogen are my reactants. That's also not CO2. My products, I've got carbon and O2, carbon and H2, and then CH3COOH. Okay, so the only reaction that has CO2 in it at all is this first one, which has CO2. Okay, so I've highlighted that. Now, the next thing that I want to do is I want to find where the CH4 is. Well, looking at my first reaction, I don't see CH4. Looking at my second reaction, I see CH4 as a reactant, which is exactly where I want to see it. And what I'm trying to do is match up of all my 3 top reactions in this particular example. I'm trying to match up my reactants with my overall reactants as well. So effectively, I found my 2 reactants, CO2 and CH4, and I placed them. I find CO2 and CH4 nowhere else in any of my reactants, or any of my reactions. Okay, my last thing to find is the CH3COOH, my product. And that is only found in my 3rd reaction. Okay, so what can I say about every single other thing in this overall reaction? Well, what I'm aiming to do with these is I'm trying to find something that's, whenever I combine these 3 reactions, I'm trying to find things that will cancel out. Okay, so if I look at reaction C, I've got 2 solid carbons as reactants. Well, and when I look at reactions A and B, I've got 1, 2 solid carbons as products. If something is in as a reactant and a product, well, that means that that's not used. So basically, I can cancel these out. So I don't care about them. Okay. Next up, I've got 2H2. Well, 2H2 is found as a reactant in reaction C, and it's found as a product in reaction B. The final reactant is O2, and I find O2 as a reactant in reaction C and as a product in reaction A. So I can cancel that out. Okay, so I found all of my reactants and all of my products. Now this particular example was set up kind of simply because I didn't really have to manipulate anything. Now the reaction that we're going to be looking at, or sorry, the last thing that I want to do with all of this information is I want to take all of my delta H values and combine them. And whenever I do that, I'm going to say 393.5 plus 74.6 plus negative 484.3 is going to leave me with a delta H that is negative 16.2 kilojoules per mole. Now I'm going to do a couple more, now we're going to go through this, but we're going to be looking at sodium hydroxide and how sodium hydroxide goes through a couple of different state changes. So next up, I'm going to give you a demonstration of what is required for this experiment, for this virtual experiment. Then I'm going to go through a couple more examples of Hess's law types of problems. I hope this is helpful, and thank you very much. All right, here we are. Hess's law experiment. Now this experiment is, it's got some subtleties and nuances to it. It's got some challenges to it. It's got everything. Now this is, and what I'm going to be doing is I'm going to be bouncing back and forth from the PDF where all the directions are and the workbench. I got 2 monitors. That's not a flex, but I'm just saying I've got 2 monitors. That's why I look now and then I look there. Okay, so I've got the PDF. We're going to be following that, but then we're going to actually do the demonstration of the experiment. Now, first and foremost, All right, let's start off the top here with the PDF. This shows our experiment. The first thing that you're going to need to do is go to this chemcollective.org/VLab/138. Okay. Whenever you're there, you're going to actually have your experiment to produce. Now, we've got a bunch of tables for this, but I'm going to walk you through everything that you need to know for all these tables. Okay, so here's my workbench. My procedure tells me that I need to do a couple of things. First thing that I need to do is go to my stockroom and go get some foam cups. I need a grand total of 3 foam cups for trials 1, 2, and 3. I'm only going to do trial number 1. It's up to y'all to do trials 2 and 3. Foam cup added. Okay. Now, the next thing that I need to add is distilled water. The next thing that I need to add is solid sodium hydroxide. Okay, I've got all these different things, and what I am trying to do is I am trying to look at the reaction of, just a second, I gotta do some shuffling of some things on my monitor, and one of my kids is about to wake up, so I'm gonna have to pause for a moment. But what I've got here is, and what I'm going to be investigating with this is, I'm going to be investigating solid sodium hydroxide, NaS, going to, oh, not Na, solid sodium hydroxide, NaOH, subscript S, going to NaOH, AQ, aqueous. Okay, and the way that I'm going to do that is I'm going to get some solid sodium hydroxide and add it to water. Now, switch to the mouse. What I'm going to do is I'm going to throw 1 gram of solid sodium hydroxide into this here foam cup. Now, what I'll notice about this foam cup is it tells me that I have exactly 1 gram solid sodium hydroxide in there, as is indicated by this species NaOH, 1.000 grams. My foam cup also tells me that it is 25.0 degrees. So my initial temperature is 25 degrees. And I mention that because we're going to be tracking change in temperature. Now, to that foam cup, I'm going to add 50 milliliters. Sodium hydroxide is a strong electrolyte. Well, it's a strong base. It's also a strong electrolyte. So it's going to dissociate. So that NaOH is going to break off into Na and OH, separate things. And that reaction is going to generate some heat. So I'm going to pour this water in here by clicking pour, and boom, there we go. What I see is my temperature has gone from 25 degrees Celsius to 30.3 degrees Celsius. Now I'm going to take you back to our PDF or our data sheet. I'm going to record some of this information. Okay, trial number 1 is basically what I've just done. And I need to get my, where is it? Comment. Nope, that's not it. There's a send for comments comment. There we go. And I'm going to minimize that. And I'm going to go to this here pencil. And I'm going to record, not with an actual pen, I'm going to record with my stylus here, the final temperature. The final temperature of this reaction was 30.3 degrees Celsius. Now, trials 2 and trial 3, those are the ones that you're going to have to do on your own. Table number 2 is the next thing that I'm able to fill in. Now, if you look here, the first column is the mass of water that's being heated. The next column is the temperature change observed. The next is heat capacity of water and heat absorbed in joules. Okay, so the temperature change observed, we know that. That is 30.3 minus 25, which is 5.3 degrees Celsius. Heat capacity of water, that is 4.184 joules per gram degrees Celsius. Okay, so what, if you haven't talked about heat capacity of water, the heat capacity of water is what, or the heat capacity of any solution or substance is what is the amount of energy that is required to change 1 gram of that substance 1 degree Celsius. So you have to input 4.184 joules of energy to change 1 gram of water 1 degree Celsius. Okay, now that grams, that's a little bit tricky though, because generally whenever I personally think about water or I think about any solution, I think, well, I think about it in terms of volume. So as Dr. Pepper, for instance, 355 milliliters.
I'm not thinking about this in terms of grams, but do we have a term where we can relate mass and volume? As my relatives from the Midwest would say, you betcha. And that is, oopsies, that is density. Now, our density, not destiny, our density of water is 1.0 grams per milliliter. Now, for the rest of this exercise, we're going to be talking about solutions of sodium hydroxide and HCl, but we're going to use that same density, 1 gram per milliliter, for all of these solutions. Okay, so the mass of water being heated. Well, we know that we're using 50 milliliters, so we're going to take our density and multiply that by 50 milliliters. So we've got 50 grams of H2O. Now I've set this table up, so all that you have to do is do 50 times 5.3 times 4.184, and that is equal to, I'm going to use the calculator on my computer, 50 times 5.3 times 4.184. And that is going to be 1108.76. Units there are joules, because remember our heat capacity was joules per gram degree Celsius. Okay, so whenever you're talking about a reaction giving off heat or absorbing heat, it's always important to think about, well, is it positive or if it's negative? An exothermic reaction, so something that gives off heat, well, that's going to be negative. If something is absorbing heat, in this case, water is absorbing our heat. Water is absorbing the heat of the reaction, and that would therefore be, well, it's going to be positive. Okay, so the next table, okay, so table 2, trial 1 is done. We're going to jump down and use something from that table 2, trial 1 in table number 3. What is the heat released in kilojoules by sodium hydroxide? Oh man, okay. So basically what that's saying is our reaction of sodium hydroxide takes place in water. Water is absorbing the heat. Sodium hydroxide is releasing the heat. And what I mean by sodium hydroxide is releasing the heat is this movement right here, this transition from a solid to an aqueous substance, that is releasing heat. And so what we want to do is we want to put that as a negative value there, okay? Now, in our previous table, we had 1108.76 joules. Now we're talking about it in kilojoules. Okay, so what we need to do with that, if you have 1,000 joules, that's the same as 1 kilojoule. So what I'm going to do is I've already put my negative sign here, but I'm going to convert this pretty much on the fly to negative 1.10876 kilojoules. Okay. That was a pretty simple conversion. I took my positive and made it a negative because I'm going from the vantage point of the water, which is absorbing the heat, to sodium hydroxide, which is releasing the heat. Sodium hydroxide is releasing the heat, therefore it's a negative value. The water is absorbing the heat, therefore it's a positive value. Okay, so I've also done that quick conversion from joules to kilojoules. The next column on table number 3 is number of moles of sodium hydroxide. Well, we know the mass of sodium hydroxide that we use, 1 gram of NaOH. We need to be able to convert that from, well, the mass that we've been provided with to the number of moles. Well, I know that the mass or the molar mass of sodium hydroxide is 40 grams NaOH. That is equal to 1 mole NaOH. You might do the calculation and figure out that it's actually 39.9998 or something like that, but 40 is fine for our purposes. So I'm going to do 1 times 1 equals 1 divided by 40, and I'll plug that also into my calculator. 1 divided by 40, that is equal to 0.025. So 0.025 moles of sodium hydroxide. Okay, now what do I need to do with that? Well, this table is set up similar to table number 2, and all that I'm doing is taking this first column and dividing it by my second column. So I'm going to take that 1.10876, I'm going to make that a negative number, divided by 0.025. And my enthalpy for this reaction is negative 44.350. Okay, so there we go. That's the, how do I put this? That is the enthalpy, the delta H for this reaction. Delta H equals negative 44.350 kilojoules per mole. Okay, now another way that you could think about this is releasing heat, this is releasing energy. If you wanted to take aqueous sodium hydroxide and make solid sodium hydroxide, you'd have to put that equal amount of energy back into it. Okay, now you have to complete trials 2 and trials 3 with those different volume or those different masses. But this is your setup and your structure for your tables. Okay, so now let's go on to part 2. Part 2 is looking at aqueous, so NaOH plus HCl, aqueous. And what's that going to produce? Well, this is a neutralization reaction. It's also a double displacement reaction, but basically it's Na ions, cations floating around, plus OH anions floating around, mixed with H plus cations and Cl minus anions. So what we're going to end up with is basically it's like switching dance partners. Na and OH, they're going to split up and they're going to pair up with Cl and H respectively. So NaCl, table salt, that's aqueous, that dissolves in solution, plus HOH, or as I like to call it, H2O. And I'm going to put a subscript L down there. Okay, so that's my reaction. Now what I'm going to do is I am going to switch my share, and I am going to resume. I'm going to clear my workbench. And whenever I clear my workbench, I'm looking at the procedure, and it has me add some other things to it. So it has me add a strong base, 1 molar sodium hydroxide. And then it has me add strong acid, 1 molar hydrochloric acid, or HCl. Okay, after that, I'm prompted and told that I need to add a total of 1, 2, 3 foam cups. Now with these foam cups, I got a little bit going on. Okay, in each of these 3 foam cups, I'm told to transfer 25 milliliters of sodium hydroxide. Okay, so I've got 25 mils, and I'm gonna go ahead and label these. You don't have to label them, but just for the demonstration and the discussion, I want to go ahead and label them. So what I need to do is just a second. There we go. Okay, so I'm going to call this one a, oh, that's not on my annotate tool yet. Okay, I'm going to call this one A, this one B. Oh, you know what? Forget that A, B, C nonsense. I'm going to call them trial 4, trial 5, trial 6, T4, T5, T6, which I think if I go with the Terminator movie series, T2 was Judgment Day, T3 was Rise of the Machines, T4 was, I can't remember. And I don't even know if they got to 6, but nevertheless. Okay, so there's my different trials. Now what I need to do is I've transferred 25 milliliters to each of these. 25 milliliters of sodium hydroxide is in each of them. Now, what I'm going to do is I'm going to add HCl. I'm going to add 10 mils of it. Because, well, for trial 4, I need 10 milliliters of it. Whenever I do that, I see that my temperature jumps up to 28.8. So that's a temperature change of 3.8 degrees. Then I've got the second trial, or the 5th trial. Well, that has me add 25 milliliters. So I got a total volume of 50 milliliters. In my 6th trial, I'm adding 45 milliliters. It seems a bit excessive, which Spoiler alert, in general chemistry, we talk about excess and limiting reagents, and that's gonna rear its head here, actually. Okay, so now what I'm gonna do is I'm gonna switch over to my PDF so I can fill in my data table. I'm gonna clear all my drawings, despite their how good they were, and I am going to go to a new share, PDF, Dunzo. This guy I'm gonna move over there, and this one, okay. Now trials 4, trial 5, trial 6. Okay. This first column is the mass of the water heated. Both these, or sorry, these are both aqueous solutions. Okay, what I said earlier was we're dealing with sodium hydroxide and HCl solutions, but we can treat them as having a density, not destiny, a density comparable to water, which our density of water is what? That's right, 1 gram per milliliter. Okay, so trial number 3 is but 35 milliliters. Trial number 4, 35 milliliters. With a density of 1 gram per milliliter, our mass is then going to be 35 grams. What was our observed temperature change there? Well, we went from 25 to 28.8, so our temperature change was 3.8 degrees Celsius. Okay. Heat capacity of water. Okay, our heat capacity of water was, and still is, 4.184 joules per gram degree Celsius. I'm going to scribble this out. I'm not going to do trials 5 and 6 calculations, but I've shown you the data, so you guys can go ahead and use that. 35 times 3.8 times 4.81 or 4.184 is equal to, again, calculator, where are you? There we are. Okay, so 35 times 3.8 times 4.184 equals, ooh, this is interesting, 556.472 joules. Okay. So now what I need to do is I need to scroll. Oh no. Oopsies, I was using the wrong function. I was not using, oh man. I got to clear my drawings. Okay, no, what I'm going to do is I'm going to write, so I'm going to write 35 times 3.8 degrees Celsius times 4.184. I'm going to make this disappear in just a second, so it'll be a little bit more clear. 556.472 joules. Okay. And booyah, it's gone. Okay, so I'm going to scroll down. Okay, so just like in our previous exercise, trial number 4 from table number 4 is going to be useful for table number 5. That was positive 556.472 joules absorbed by water. What do we know about this? The sodium hydroxide and the HCl, their neutralization of one another, that's where your reaction is going to take place. So that's going to be releasing energy. So that's negative, and we're converting to joules, so it's negative 0.55647.2. Okay, now, number of moles of sodium hydroxide. We had a 1 molar solution of NaOH. Okay, we used 25 milliliters or 0.025 liters. Okay, so when you take the concentration, moles per liter, and multiply it by the number of liters, you're going to get the number of moles, which is 0.025 moles. Okay, now the next column, it might seem a little bit confusing. Number of moles reacted in foam cup. What gives, man? Huh? Is this the same thing? It's not. How do you know it's not? Because we're talking about limiting and excess reagents here. So NaOH, we know that we had 0.025 moles. And I figured that out by taking my concentration of that solution times the volume that was utilized. Okay, sodium hydroxide reacts with the HCl solution. That HCl solution, let's talk about that one. That was a 1 molar HCl solution. And what was the volume of that? We use only 10 milliliters of it, so 0.010 liters. So that would mean volume times your concentration is 0.010 moles. Okay, now when we look at a neutralization reaction between, I'm going to write down here, NaOH and HCl. Actually, you know what? Did I write it up earlier? I wrote it earlier. Okay, when I look at this reaction, this is a 1-to-1 molar relationship. So 1 mole of sodium hydroxide perfectly reacts with 1 mole of HCl. Okay, now 0.1 moles of sodium hydroxide. How much HCl does that need? That needs 0.1 moles. Okay, so then when we scroll down and we look at 0.025 moles of sodium hydroxide, needs exactly 0.025 moles of HCl. Do we have that much? No, we don't. We have less than that. Therefore, we can identify HCl as a limiting reactant. Although we provided 0.025 moles of NaOH to this 0.01 moles of HCl, only 0.01 moles of HCl is going to react with the 0.025 moles of NaOH. So what does that mean? That means that, well, there's excess. How much excess? Well, you could say 0.025 minus 0.010. So approximately 0.015 moles NaOH. Okay, so that means there's both sodium ions freely floating around and hydroxide ions freely floating around. Okay, so what that means though is this as the limiting reactant, that's going to tell us how much of our sodium hydroxide is used. So even though we provided 0.025 moles of sodium hydroxide, only 0.01 moles or 0.010 moles are going to react in our cup or in our foam cup there. So now what we need to do is again take this column right here, negative 0.556472, and divide it by this column right here. We can disregard this middle number of moles of sodium hydroxide. So what you need to do in these trials is you need to figure out which is your limiting reactant. Spoiler alert. What happens in trial number 5? Well, we put an equal amount of sodium hydroxide as HCl. Both of the solutions are 1 molar, so there's not going to be a limiting reactant there. Another spoiler alert. In our 6th trial, we put 45 mils of HCl compared to 25 mils of sodium hydroxide. So which is going to be excess there, the HCl or the sodium hydroxide? Okay, just think about that, because that will be something that you'll have to fill in for tables 5 and 6, or trials 5 and 6, I'm sorry. Okay, so now what I'm going to do is take my 0.556472, make that a negative number, and I'm going to divide it by 0.010. And I get a number that is negative 55.6472 kilojoules per mole. Okay, so now what I've got and what I can look at is I've got the delta H for this reaction. Oh, wait, I don't need to put a 0. I've got 1 delta H for this. I'm going to get another delta H. And I'm going to need to come up with an average enthalpy for the reaction of this, well, mixture of 2 aqueous substances. So what we can say is that there's some amount of heat. I'll just use my one data point, negative 55.64, I'm going to call it 65 kilojoules per mole. There's some heat released when you neutralize NaOH or HCl with NaOH. Okay. There's also heat released when solid NaOH goes to aqueous. So that transition from solid to aqueous, this is one of my kids is waking up. Okay, he's still napping. His eyes are open. Anyway, he's 5 months. Okay, he's 5 months old. He's asleep right now, but he's stirring. Okay, so the last part of this, the last reaction that I'm going to look at, We've talked about a phase change, solid to aqueous. And then we've talked about a neutralization. Now we're going to combine their powers. And we're going to say, what is the enthalpy change? What is the delta H of solid NaOH being neutralized by HCl aqueous? Okay, what's going to happen at the end of this? Well, in theory, we're going to have a bunch of NaCl. We're going to have some H2O. That NaCl is going to be aqueous, and that H2O is going to be liquid. But let's think about this. We've got two things going on. We've got the phase change and the heat associated with that, but we've also got the neutralization. Okay, so what I'm going to do is I'm going to jump over to my other screen. New share. Okay. I'm going to clear my workbench. It's always good to have a clear workbench. It's nice and clean and safer. Uh-oh, I might have to pause because this rascal's waking up. Okay, so I've cleared my workbench. And what I'm going to do is I'm going to add that solid. Did I start the new share? I did. Great. That's great news. I'm going to add my foam cup. I'm going to do a total of 4 trials here. Foam cup, foam cup, foam cup, foam cup. Then I'm going to get, remember, aqueous, liquid HCl, but I'm going to do 2 different things. I'm going to use 1 molar HCl and 0.5 molar HCl. The last thing that I need to add, sodium hydroxide. Okay. I've got a series of trials here. Trial 7, trial 8, trial 9, and trial 10. Okay, trial number 7, which I'm going to write. I'll be back. I got to pause this. All right, I'm back. And what I'm going to do now is I'm going to do this reaction where I'm looking at, do I share this? Okay, good. I'm sharing the right thing. Where I am looking at different masses of sodium hydroxide reacting with different solutions of HCl. Okay, so the first thing that I want to do is I want to put trial number 7, which I'm going to go ahead and come up with some quick labels for these guys. This guy is number 7, 8, 9, 10. Okay, so number 7 is going to be 2 grams of solid NaOH plus 50 mils of 0.5 molar HCl. Trial 8 is going to be 2 grams, or no, I'm sorry, it's going to be 4 grams of NaOH plus 50 mils of 0.5 molar HCl. Okay, now, before we get too far away from this discussion, let's talk about this. 2 grams of sodium hydroxide. Well, our molar mass of sodium hydroxide is 40 grams per mole. Okay, so we've got 2, 41. So we're talking about, what would that be? 2 divided by 40. I'm going to use my calculator for this. Calculator. 2 divided by 40. Got 0.5. So I'm talking about 0.5 moles NaOH. Okay, sounds good. Now we've got 50 milliliters of 0.5 molar HCl. So that would be 0.5 times 0.05. I converted this is my volume in liters. 0.5 times, let's clear that out. 0.5 times 0.05, and that would be 0.25. Wait. Sorry, I made a mistake, but 0.05 moles of sodium hydroxide. 0.025 moles of HCl. Okay, so what we're looking at here is when we mix these two things together in trial number 7, we have 2 times as many moles of sodium hydroxide as we have number of moles of HCl. So we can immediately say that there's a limiting reactant there. And, spoiler alert, limiting. Okay, now is that going to have an impact on the overall reaction? Well, it remains to be seen. For trial number 8, 4 grams, it's going to be 4 grams of sodium hydroxide is going to be 0.1 mole NaOH. It's again 50 milliliters, so we're looking at it's again 50 milliliters of that 0.5 molar solution, so 0.025 moles HCl. Okay, so trials 7 and 8, in both cases, HCl is going to be limiting, and all that we're doing is we're increasing the amount of sodium hydroxide between the two of them. Now, what we want to know is we want to know how this. All right, so HCl is going to be limiting in both cases, but let's think about this. HCl, that's an aqueous solution. Sodium hydroxide is solid. So we're expecting that, well, 2 things are going to take place. One of which is that sodium hydroxide is going to dissociate into sodium ions and hydroxide anions. What's going to happen to those sodium ions and hydroxide anions? Well, they are going to react with the hydrogen ions and the chloride ions. So we're kind of going to have 2 things taking place. We're going to have our neutralization, which we've already seen the neutralization produces some heat, but we're also going to have a dissociation reaction, or that sodium ion breaking down into sodium and, our dissociation of sodium hydroxide from solid sodium hydroxide to those individual cations and anions, respectively. So keep an eye out for that. We're going to have these 2 different things. It's important to recognize that because we don't know if that's going to have an overall impact on our reaction and the amount of heat that's generated. Okay, now with that said, I'm going to clear my drawings here. And what I'm going to do is to foam cup over here on the left, which I previously labeled 7, I'm going to add 2 grams of solid sodium hydroxide. I'm going to put that right here. To this one, I'm going to add 4 grams of sodium hydroxide. Okay, now I'm going to take my HCl solution, and I'm going to add 50 milliliters of that 0.5 molar HCl. Okay, I see a heat there. I see that goes up to 42.3 degrees Celsius. Now, the next one, where I basically just have more sodium hydroxide. I see whenever I add 50 milliliters of HCl to my 4 grams of sodium hydroxide. Well, I see, again, I can get rid of that. My temperature jumps up to 52.9 degrees. Okay, so now I'm going to change my screen, and I'm going to document all this. Wait just a second. There we go. I'm going to share this screen with y'all. And then this screen I'm going to move so that I can keep an eye on it. Okay, so, okay, the mass of the water being heated. Well, again, this is a 50 milliliter solution, and we're going to treat that as having a density similar to that of water. So I'm going to write 50 grams for all of these. I'm just going to go ahead and save myself some time. 50 grams of each of these different solutions. Now, my observed temperature change. Well, I'm going to go ahead and do 42.3 degrees Celsius. And I got to be honest, I'm going to walk you through all of these because this is a little bit trickier. This is a trickier part of the exercise. 52.9 degrees Celsius. Okay, well, I'm doing that wrong. Huh. Okay, what was my temperature change? It went from 25 to 42.3. So that's a temperature change of 17.3 degrees Celsius. 52.9, that's a temperature change of 27.9 degrees Celsius. My heat capacity of water is 4.184 joules per gram degrees Celsius. This is just like the tables we've seen previously. Multiply all these by one another. Oh, I forgot to put a 0 there. And the heat absorbed is going to be 50 times 17.3 times 4.184. I'm going to get here 3,619.16. Well, 316.9, there's 3,619.6 joules. Okay, the next trial. My next trial is 50 times 27.9 times 4.184. I did that right. And that is 5,836.68 joules. Okay, so what we see there is we see as the amount of sodium hydroxide goes up, so too does the amount of heat that's absorbed by our solution. All right, now I'm going to scroll down. We're going to tackle trial 7 and 8 first, and then we're going to go back and do 9 and 10. Okay, so this is again similar to what we've seen previously. Use table 7 and table 8, or sorry, use table 6 to fill in table 7. So the heat that's released is negative 3,619.16, but I'm going to make that 3.61916 kilojoules. Okay, number of moles of sodium hydroxide. I just did that calculation. I wish I wouldn't have erased it all, but let's see, that's 2 grams divided by 40. That 40 comes from our molar mass, and that's 0.05 moles of sodium hydroxide. Okay, now the number of moles that reacted in my foam cup. Well, I had, let's see, 0.05 moles NaOH that reacted with 0.025 moles of HCl. Okay, so that, I looked at that and that was, well, 0.025 moles of HCl was my limiting reactant. So I actually kind of had there, well, 0.025 moles of HCl. But let's think about this. We had 2 things going on here. So I had a couple of different things going on here, but you know what? I'm just going to go ahead and write in the 0.025 moles because, well, one thing that I had taking place was I had the neutralization reaction. But then I also had to think about, well, of the 0.05 moles of sodium hydroxide, whatever is not neutralized by HCl, well, that's going to dissociate. So there's going to be heat related to that. So I've got 2 factors going on here. So my enthalpy of reaction here is a little bit complicated. Now, what that means though is whenever we're going to get to that in just a moment, but what I can write right now is that this enthalpy of reaction is negative 144.766 or 7664. But keep in mind that that number is reflective of both the dissociation, or the heat produced by the dissociation of some of the sodium hydroxide, as well as the neutralization. Okay. Now, I want to go ahead and fill in the remainder of this table that I can so far. So that's negative 5.836.68 kilojoules. There's 5.83668 kilojoules. Okay, number of moles of sodium hydroxide that were in here. Well, this is 4 grams, and that would be 0.1 moles. Number of moles reacted in my foam cup. Okay, so this is again 50 milliliters of a 0.5 molar solution. So it's still 0.025 moles. Okay, so now what I need to do is say, well, 5.83668 divided by 0.025. That gets me negative 233.467 kilojoules per mole. Now, if you filled in the rest of these tables, well, This is a little bit surprising because our enthalpies of reaction, well, generally, you're not going to notice that much of a difference, especially if you look like at our neutralization. That amount or that number they were fairly comparable to one another. This is kind of weird though. But remember, we've got two things taking place. Sodium hydroxide. Some of it is simply dissociating into solution. Some of it's being neutralized. So we have to take that into consideration. So what would be the best way to figure out what is the enthalpy of the reaction for the neutralization of a specific amount of sodium hydroxide? So you're only looking at that sodium hydroxide being neutral, that solid sodium hydroxide being neutralized by HCl. Well, I think the best way to look at that would be to put an equal molar amount of sodium hydroxide and HCl in that solution. So now let's look at trials number 9 and 10. Trials number 9 and 10. What I was doing was I would take 2 grams of sodium hydroxide in 1 cup, 4 grams in another cup. Okay. Then I'd take 50 milliliters of my 1 molar solution. Then 50 milliliters of my 1 molar solution and mix it with the other substance. Okay. What I see here is my temperature has gone up to 48.9 degrees Celsius and 59.5 degrees Celsius. But we need to unpack this a little bit. Okay, so we've got, let's see, in this one, 2 grams of sodium hydroxide. That would be 0.05 moles NaOH in this one. So this would be trial number 9. Trial number 10, we're going to have 0.10 moles NaOH. Okay, so I'm going to write this on a separate piece of paper because I'm going to make this disappear in just a moment. 9, 10, 0.05, 0.10. Okay, so now what I need to do, I've already got the temperatures there. I need to think back to, well, how much HCl did I add? So in foam cup number 9, or trial number 9, I had 50 milliliters, or 0.05 molar HCl times, or sorry, liters, 0.05 liters of HCl times 1 molar. That's going to give me 0.05 moles. Fantastic. Trial number 9, I'm going to have a perfect molar ratio there. 0.05 HCl and 0.05 NaOH. So if anything, this is going to be the best way to evaluate this reaction. Anything else, I have excess, or I have an excess reagent, or I have a limiting reagent. In this case, I've got a perfect molar ratio. Okay. Now what I want to do is I want to go ahead and clear my writing here. And I want to switch my screen. Okay. Now I've got all my data on my other screen, so I'm just going to look at that and transcribe it. Okay, so for trial number 9, I saw a temperature change, and that temperature change, there we go, minimize, yep, that's good. Okay, trial number 9, my perfect molar ratio, I saw my temperature go up from 25 to 48.9 degrees. So that would be 23.9 degrees Celsius. Okay. Heat capacity is the same. Trial number 10, I saw my temperature jump up 59.5 degrees Celsius. That 59.5 degrees Celsius, that is a change of 34.5 degrees. I believe that is correct. Now what I need to do is figure out the heat that is absorbed in this reaction. Okay, so 50 times 23.9 times 4.184. And I get 4999.88 joules. Okay, trial number 10. Trial number 10 is 50 times 34.5 times 4.184. Okay, so that's 72.17.4 joules. Okay, good. I've got some numbers that I can work with. So I need to copy all this information, and I need to think about what I'm doing with this. So this is the heat that's absorbed by the water, therefore the heat that's released by sodium hydroxide. So for trial number 9, that's going to be negative 4.99988 kilojoules. For trial 10, that's negative 7217.4. Sorry, that's 7.21740 kilojoules. For trial number 9, what's my moles of sodium hydroxide? It would be 0.05. Okay, for trial 10, that's 0.1 moles sodium hydroxide. Now, what is the number of moles of sodium hydroxide that is reacted in my foam cup in trial number 9? Well, that's our perfect molar ratio. That's 0.05 moles. Now, in trial number 10, how many moles of sodium hydroxide are reacted in my foam cup? Well, that's going to be 0.05 moles. Now, you might be looking at this and thinking, wait a minute, what's happened? Well, think about trial number 7 and trial number 8. Trial number 7 and 8, they used a 0.5 molar solution. Trial numbers 9 and 10, they used a 1 molar solution of HCl. So our concentration of HCl between trial 7 and 8 and 9 and 10 went up. Therefore, the amount of sodium hydroxide that was reacted also went up. Okay, so now what I want to do is I want to figure out approximately what's the enthalpy of the reaction for trial number 9 and trial number 10. Trial number 9, I'm going to do 4.99988 divided by 0.05. That's going to give me negative 99.9976 kilojoules per mole. These numbers are just all over the place. But that reaction right there, that's my perfect molar ratio. The exact number of moles of sodium hydroxide and the exact number of moles of HCl are equal to one another. I don't have any excess sodium hydroxide. Trial number 10, what do I have? I've got excess sodium hydroxide. Okay, so now let's see how this impacts my result. So 7.21740 divided by 0.05. And I get, oh, well, this is funny, negative 144.348 kilojoules per mole. Now this gives us 4 data points that are kind of all over the place. 2 data points that are pretty similar to one another. Trials number 7 and trial number 10, they're pretty similar to one another. Trial number 8, I don't even know what's going on with that one. But when I look at trial number 7 and number 10, actually trial number 7, 8, and 10, what stands out to me is that, and I'm going to put another star by that, not molar ratios. In these 3 trials, 7, 8, and 10, you've got 2 different things going on. You've got the dissociation, which we've already seen that dissociation has heat generated. You've also got the neutralization. So you've got this neutralization event where HCl and sodium hydroxide are going to mix up. They're going to knock one another out. But then you also have the secondary, I guess kind of a secondary reaction where additional sodium hydroxide is going to be dissociated. Okay, so if we wanted to look at just the neutralization of that sodium hydroxide, we'd want a perfect molar ratio, in which case we would want trial number 9, because that gives us negative 99.76 or negative 99.9976 kilojoules per mole. Okay, so this right here, I'm going to put a smiley face by it, because that's the number that we want to see. Now, I hope that makes sense. The key is there is nothing in excess. Okay, now the purpose and the intent of this exercise is that Hess's law basically says that if a reaction occurs in multiple steps, the enthalpy of that reaction is equal to the sum of the enthalpy of the steps. Okay, so what we want to look at here is we want to look at our 3 different reactions, and we want to see if these reactions have relationships between one another. The first reaction that I'm going to write down here is my step number 1. NaOH, solid, being converted to NaOH, aqueous. Now I had an enthalpy of a reaction there, a delta H that was approximately, let's call it negative 44. That's a 4, not a 9. I'm going to scribble this out because it just looked worse. Negative 44 kilojoules per mole. Okay. What other reactions did I have where I talked about solid sodium hydroxide? Well, my last reaction was my solid sodium hydroxide, which was NaOH, solid, plus HCl, aqueous, being converted to NaCl, aqueous, plus H2O, liquid. And the number that I want to use there, well, I've got 3 different numbers, but I know which one I want to use. It's that negative 99.99. The reason for that is I have a perfect molar ratio. So I'm going to look at that and say negative 99.99 kilojoules per mole. Now, Hess's law says that I can manipulate these reactions, these 2 steps of my reaction, to come up with an overall reaction. And my third reaction of the 3 reactions that I did, the second one that I did was NaOH, aqueous, plus HCl, aqueous, yields NaCl, aqueous, plus H2O, liquid. All right, now looking at the different steps here, do I see aqueous sodium hydroxide in either step 1 or step 2? And I'm going to switch to a highlighter. I'm going to switch to an orange highlighter. That seems like a good highlighter color. I hope I don't just mark it out altogether. Wait, it didn't even work. Okay, let's see if this will work. Nope, I just crossed out my numbers. I didn't want to do that. I'm going to delete that. I'm going to try my highlighter again. Is that how I do it? Is that how I do it? Let's see what happens here. Well, that's not what I want to do at all. Control Z. You know what I'm going to do? I'm going to switch to my pencil. I'm going to go to orange. I'm going to underline it. Okay. Do I see sodium hydroxide aqueous? And that phase is very important. Do I see that in step 1 or step 2? I do. I see it as a product in step number 1. Okay. Aqueous HCl. Do I see that in any of my reactions? Ah, lo and behold, I do. I see it as a reactant in step number 2. Okay. Do I see aqueous NaCl and liquid water as products? I do. I see them as products in reaction or step number 2. Okay. So of the, what would that be? 6 different things, two things in step 1, 4 things in step 2. I've got 2 things that I can't account for. Sodium hydroxide solid in both steps 1 and steps 2. Now, Hess's law is fantastic because what we can do is we can say, well, if the transition from solid sodium hydroxide to aqueous sodium hydroxide releases 44 kilojoules per mole, well then this right here, NaOH, solid going to NaOH aqueous, we know something about the delta H of that. It's positive 44 kilojoules per mole. So what we did there was we said, well, solid sodium hydroxide, we see that as a reactant in both steps 1 and steps 2. So what we did was we took step number 1 and we gave it the Missy misdemeanor Elliott treatment. We flipped it and reversed it. And when we flipped it and reversed it, we rewrote our delta H as a positive value rather than a negative value. But now I realize I made a mistake. This should be aqueous. And this should be solid. Because now what we can do is we can combine steps 1 and step 2. And we can say, well, if something is a reactant in step 1, or I'm sorry, if something is a reactant in one step and is a product in the other step, effectively, we can cancel it out. So I'm going to cancel out sodium hydroxide. And so then I can use the heat of these 2 reactions to come up with my delta H for this 3rd reaction. And this delta H for this 3rd reaction is ultimately, let's see, positive 44 plus negative 99 is going to be about negative 55 kilojoules per mole. Okay, so what we're doing here is we're looking at what is the heat of 2 of our reactions, and we've already determined the heat of that other reaction. We already have an empirically or experimentally determined delta H for this, and that delta H is approximately negative 56 kilojoules per mole. So basically what we did was we did all 3 of these reactions, and then we said, okay, well, let's try to use 2 of them to prove Hess's law and then compare it to our data that we've generated. And so what we can do is we can say, what is the enthalpy of a reaction in kilojoules per mole from table 8, where we're looking at aqueous HCl and aqueous sodium hydroxide? Table 8, that would be approximately negative 56. Okay. Or actually, no, that would be our calculated. So that's negative 55. What's the average enthalpy of reaction in kilojoules per mole from table number 7? Well, table number 7. Actually, I believe that's a typo there. Yeah. What we want to do is not this one. Instead, what we want to do is we want to compare our theoretical value, negative 55 kilojoules per mole, to our empirically determined value. So you're going to take these 3 values, figure out the average. Here it's negative 55.6472, negative 55.6472, and what we're looking at is a difference of 0.6472. So we're comparing a theoretical and an empirical value. So essentially, we've kind of validated or proven Hess's law based on doing this reaction, mixing aqueous HCl and aqueous sodium hydroxide, Then looking at the phase change of sodium hydroxide in water and looking at the neutralization of solid sodium hydroxide. Okay, I hope this was helpful. It's a little bit challenging because trials 7 through 10, they presented a whole different issue to us. But the important thing is with that one, we are concerned with a molar ratio, a 1-to-1 molar ratio. Are we not concerned with that in the previous? So in part 2, are we not concerned with that? No, we're not. The reason is because we have no phase change there. We have no solid going to an aqueous. We have the formation of water, but we have no phase changes taking place there. All right, well, I hope this is helpful. What you're gonna need to do is complete the quiz that's posted on your Canvas page. So take all the pictures and everything like that. I hope this illustrated Hess's law pretty well. Those phases are very important to keep track of. And well, I hope y'all have a good one.